Hey guys, today I created more advanced Unity video. I will talk about how to bake animations into textures, and after that use the texture in our custom vertex shader to move the mesh. This will optimize speed on CPU and move that work to GPU. We will create our custom compute shader and surface shader, so basic knowledge is required. But don't worry, it's not as hard as you might think. First, we will start with new project, create new project, set it to 3D and name it whatever you want. I name it crowd instancing. Instancing. I will prefer this one and hit create. I will skip the import part. So I imported my model from asset store. You can find it, audience ground, it's free. It's made of one mesh and one material, so it will help us. You can use your own model video animation, but the first thing we need to do is create our own compute shader. Compute shaders are simply to set up, and this tutorial should be accessible to anyone who has worked with the Unity shader system. However, compute shaders are not simply to use correctly. Identifying the right place and format to ship the data to GPU for processing is an art that is far beyond the scope of this video. Well, unlike a vertex and fragment shader for materials, image effects, etc., a compute shader is a body of code executed in a parallel on the GPU that accomplishes a direct task quickly. It does this by utilizing the large volume of threads available on the GPU for work on a single repeated task. Inside the Unity 3D engine, a computer shader will be running using HLSL. Let's begin working with a compute shader. Each compute shader has two parts, the compute shader code and the CS marshalling class that goes along with it. The marshalling class is optional for every shader, but at least one script must exist to actually send the data to the graphics card and run the shader. I forgot to mention how our baked animation on texture will look like. One texture is one animation, each row is one frame of animation, and each column is vertex for position or normal. So for each vertex we set RGBA value to correspond our vertex position and normal. Let's go ahead and create a compute shader by right clicking inside assets and going create shader, compute shader, and name it mesh info texture generator. Open it. Our shader will get vertices and normals data and transfer the data to render texture. So we will define our output textures, RV texture 2D. That would be float and it would be out position. And once again RV texture 2D and out normal. These are our render textures. RV means that read and write, without it you can only read from variable. For right calculation of vertex position on render texture, we need to have access to mesh vertices position and normals. We're gonna create int vert count, so we need to know how many vertices there are, and we will create struct. I will call it mesh info, and it will have float position and float normal. Let's get into why compute shaders are super awesome. The ability to marshal custom data from the CPU to GPU. This is especially useful when trying to perform complex operation on the GPU that requires data types of some form. We will use structured buffer to hold info about our mesh vertices. So struct thread buffer mesh info, and we will call it mesh info. For read and write version, you need to use RV structured buffer. Number of threads is where the threads are defined for the group that the GPU will spawn for the shader. The threads are spawned accessed like an array of 1 to 3 dimensions. So in this case, since we say numbers 8, 8, 1, it defines a thread group of 64 threads accessed like a 2D array since the X and Y dimensions are specified. Identifying how many threads to work with is complicated and relies heavily on your situation and platform. Inside of signature of the function we have ID, svdispatch thread ID, which is a set of 3 unsigned integers, accessible with X, Y, and Z, defined by GPU through svdispatch thread ID, as we can see here. svdispatch thread ID is the set of indices associated with the current thread inside the thread group as an array. So if I am the first thread inside the 2D array group, my ID data would be 0, 0, X equals 0, Y equals 0, according to svdispatch thread ID. Note that as said earlier, every compute shader needs a shared marshalling class that goes along with it. So we need to create one. Go to Unity. Oh, there is error. Float free, sorry. And I will comment this because we don't need it now. Sorry. So go in Unity and create new script. Call it Animator Texture Baker. Baker, please, with capital B. And open it. Fix the name. And so remove the update method because we don't use it. And create new coroutine Animator bake animation. And your return now for the simplicity and start the coroutine. Yeah. So what will be bake animation method do? I will use animator component and skin mesh renderer component. It will find every creep in animator, and per frame of animation it will get mesh from skin mesh renderer and set values to our custom mesh info structure after we send data to the compute shader. That will create rendered textures from our animation. We will then convert the rendered texture to texture 2D so we can use it in our custom vertex shader we will create later. So let's begin. We need Animator, and we will get component Animator. The actual clips from Animator using runtime we can get like this: work clips, Animator, runtime, sorry, Animator, Animator, runtime, Animator controller, and animation clips. We need the skin, so var skin equals get component, and we will get it in the child, and it's skin mesh renderer. Now we can count the vertices, so we vertex count equals skin get the mesh, to mesh, and vertex count, yeah. Now we need to create new mesh that will store our data per frame. So var mesh new mesh. Now we can, well, now we need to stop Animator from running itself. Animator speed equals 0. So now we can calculate texture white because we have already texture white. It will be math next power of 2 from vertex count, because remember the rows are our vertices. Now we can, for each clip, for each clip in clips, we will find how many frames it got. Math of 2 next power of 2. We can calculate it by C clip length, and I will take 20 frames per second. It should be 0.5. Frames will represent our rows in our texture 2D. So as I told you, we will need structure. It should be the same as in our compute shader. So structure should be public structure vert info. The naming is not important, but actual data types are important. Position and public vector free normal. Now we can create information about the clip. Info list that equals new list of vertex info. And now we need to create 2 render textures that will store data from compute shader. So var position render texture equals new render texture, texture white, number of frames, depth should be 0, render texture IRGB half, the texture format, sorry, should be like this. And we will duplicate this line and create for normals same texture. For simplicity, name it string format, and it will 2 variables inside position texture, and it will be name and name of the model and the clip name. So we need to know which object it belongs to, and we will duplicate this, and we will do same for normal texture. We need to set up this for each little trick if you have more than one variable, but not in array. You can create the array and iterate over it. So rt in new array that will belongs to prt and nrt. Render texture, we will enable random write, so we can write from compute shader. We will create the render texture. We will set the global texture to active to our render texture. We will clear the render texture. Yeah. True background color clear. Yeah, that should be right. Now we can start playing our animation and wait for the next update. So animator play, clip name, and plays the current state. So we will name our states in Animator same as the clip in the state. It would match, and the yield for the next frame. And when it starts, we for I is less than number of frames plus. We set the animator to exact time. Animator play, C name, layer 0, and normalized time should be in float, as I write, yeah, and number of frames. And wait for the next update so we can get baked mesh, skin baked mesh to our mesh, and we need to add these values to our info list. So info, add the range for every vertex. We will do the same. Will range using system limit range, and from 0 to vertex count, the number of vertices is the same. We select ID to new vert info, and position of new vert info should be position mesh vertices IDX. Take that, and normal should be the same, mesh normals, and it should be like this. Now we have our vertices and normals in our info list, so we need to somehow send this data to compute shader, and we need to allocate space for this data. So we will create buffer, new compute buffer with info count as a number of, and stride should be system runtime interrupt services marshal size of vert info, and this should be type of, probably, yeah, type of, yeah, that's good. Now we can set the data, set data, and pass our data. We forget to use reference to our compute shader, so compute shader, and I will name it info text generator. This will be better for you, so I will kernel equals info texture generator. We need to find the kernel, so kernel cs mine, as we are telling here, yeah. So we will find the kernel. We need to find number of threads, x, y, and z. Info text generator get kernel thread group sizes. We will pass the kernel out x, out y, and out z, yeah. And we will get 8, this will be 8, 8, and 1. We set these values to the compute shader, so info text generator set int. These names should match the names in compute shader, so vert count should be same as vert count, yeah. And we set v count. Now we set buffer. This is our structure buffer. Set buffer. We need to specify the kernel. Name is info, probably mesh info. And not dot line to set the buffer, so that's right. And for the output we need to set our render textures that we created earlier. Set texture, we'll select kernel, and it's out position PRT, and out normal. So now we can dispatch the shader, so every thread knows its x and y in render texture. So info text gen dispatch kernel number of vertices, and we need to know how many times we need to call that exactly. So we got 64 vertices, 8 threads, so we need to call it 8 plus 1 time. Same for the frames. So frames, I think it should be int because we set it as int y plus 1, and we can pass here z, yeah. That should be 1. And now we can release the buffer because the computer is done. Buffer release. Open our computer again because we didn't insert actual code here as to do says. We need to know our index. We are passing 1D array, but we are getting x and y coordinate of that, so we need to find it. So it's easy. id x, id y, create vert count plus idx. Now we can find our data. So mesh info mesh info at our index, and we need to save that to render texture. So out position idx y, so it will do it in x and y coordinate, and we need to set to float 4 because it's RGBA, so 4 values, but position is only in 3. So info dot position and 0 1, and same for info dot normal. This is float 3. We need to float 4 out normal, and that's all for compute shader. This should work now. When we release the shader and buffer, this compute shader, it renders the outputs to render textures, but we can use render textures as texture 2D, so we need to convert it. I will help you to convert render texture to texture 2D. Create new function convert that will take our render texture, public, it will return our texture 2D and not the name, and the name would be convert, and it will take render texture. First we need to create new texture that will equal to new texture 2D. It will have same width and height as our render texture, so width and RT height, and format will be as we render texture format RGBA half, yeah, and we don't want to create mil maps, so make it false. Return texture. Now we need to read the pixels from the render texture, and the render texture active will be our render texture 2D read pixels, and we will pass the rectangle min max rectangle with 0 0 RT width and RT height, and we will make it to 0 0. So our first pixel will be, and now we can set the render texture active to false. No, false null, sorry. After this release, we need to set if and if, because we can do it only in editor and you can build it without it. We will create a position texture and convert our render position render texture. Sorry, PRT should be, yeah, and same for normal texture. Now we need to copy actual data from the render texture to our texture. So to do so, we can use graphic texture, yeah, and it will take PRT and destination is our position texture, and same for normal render texture and normal texture 2D. So we have our render textures converted to a texture 2D, and we need to save that to our assets. If you didn't do it, there is a handle asset database. So we need to import because it's in Unity editor, and we can create asset. It will be our position texture, and name would be path combine import using system IO, and it will be assets, and name of our render texture that name plus dot asset. And same we can do for our normal texture 2D. Assets on RT. Now we can asset database, save these assets, save assets, and refer to the database. Cool. This is everything we will do here, and I think it should be good. There is one simple error. What's wrong with this? Out position. Yeah. Sorry. Yeah. Position. Oh, but here our model. Look at him. How cute he is. Want to use grid. Yeah. He has no animator, so add animator, and this is legacy. We will use the humanoid rig, some warnings, but that's not important, and some animations. Okay, he needs avatars, so we will use his avatar, and for audience we will create animator controller. So audience animate controller, and we will pass it to our audience. Cool. Save the scene, open the animator, and create new state, and call it idle, or same as your animation name, and use the eyes. Okay, now we will attach our new script, animation texture baker, and our compute shader as a reference, and try it now. You can see it will go every frame, but it should be fast for this simple animation. Nice. You can see the baked animation here. All his vertices, you can see the changes in vertex position, and this is normal, and in vertex it's looking like this. Yeah. Cool. Last thing we need to do, guess what? We need to create our shader. Yeah, that's right. So create new shader, standard surface shader, vert anim shader. I will make it simple, so custom remove this code, properties, and subshader. Cool. We will need mine texture, that should be texture 2D, and default will be white. After that we will pass there our position texture, always be 2D black, and normal texture 2D, not 3D, 2D. Creating new dimensions, it would be white. Now we can create length of the animation, so we can control how fast it will be played. Animation length, it will be float, set it to 1. What can we do? We can create DT called delta time. It will offset our animation. Delta time. Create float. Equals, yeah. Now let's begin with our shader. We need to create path, CG program, and CG. We will have our own vertex and fragment fragment functions. So pragma vertex equals vert, pragma, this is fragment frag. I couldn't stay in the same place. And we will include, as always, unity CG, it's bins, yeah. We need to know the value and the texel size of the position texture. So if you define texel size, we need it should be the same as this, so position texture, and followed by texel size. And now we know the texel size. The data that will be passed to our vertex or up data, and it should be our UV. So that's text chord 0. I hate this. It should be float, yeah. Float 2. Now we need to pass data from vertex to fragment shader, so frag vertex to fragment, and it will have float to our UV, text chord 0, and it should have this one, yeah. Float 3 normal, that's texture chord 1, and float 4 position, that's vertex SV position, yeah. We need to create sampler 2D for our main texture, main text, position texture, and normal texture, NML text. And we need to have texel size, as I mentioned, texel size from our position texture, and we will define length and delta time, yeah, that's right. Now the magic begins. Vertex to fragment, vert, pass there up data v, and do int with s is our vertex id, text id, yeah. We need to calculate where we are, so float t as time will take time from shader minus delta time, so it's shift, and based on length. I will loop these animations, so I will use F mode, so the F mode T1 1. This will loop our animation. Sorry, yeah. Now we need to calculate our X position on texture. So X would be equal to vertex ID plus 0.5 plus our texel size X. Our E value should be the T, as I'm not mistaken. Now we can calculate our position of the vertex. So position should be text to with function text to the LOD. We'll take from our position texture with our position of X, Y, 0, 0, because we want the maximum quality, and same for our normal equals text to load and ML texture. Create new vertex info and set the vertex equals clip the position, so unity, how is that object to clip position, And for normal, we need to convert it to world normal. Yeah, Unity object to world normal, and we will pass that our normal. UV should be our UV, and we can return fragment shader half. For fragment shader, we will take value 2 as input, as we target. We will use half because it's okay. Here we will calculate the normal. In normal is always float 3, 0, 1 dot 0.5 is 0.5 because of the exercise, and yeah, half for call should be text 2D mine texture it RUV cool, and return div multiplied by call. This should be it, yeah. Check Unity if we have some errors. So I found the error. Error was the exercise should be multiplied with vertex ID, and I forgot to set these to float. For go to Unity and let's go. We can see this is only mesh, but it's animating because of our shader from our vertices. So thank you for the time, because it was a really long tutorial. See you in the next video. Maybe I will do GPU instancing video next time. Thank you for watching. Bye.